Okay, so last time we talked about solving this set of equations in two unknowns, x1 and x2, in terms of the value of these two linear functions that were equal to y1 and y2. So you give me a value of the function, y1 and y2, and I tell you what x1 and x2 are. Sometimes that's called inverting the set of equations to find the inputs. All right. We can use a special, and here are solutions to that equation down here, those equations down here. These solutions apply so long as this thing in the denominator, AD minus BC, doesn't equal 0. That thing in the denominator is called the determinant, and it determines whether or not you have a solution to these set of equations with the standard technique. If the determinant is not equal to 0, then you do have a solution. If the determinant is equal to 0, then you need to look back at your equations, and there probably is a different kind of solution already sitting there. We're going to see in a special case that the determinant equals 0 case is a really important one. But the topic of this little video is how we make a matrix equation out of this set of non-matrix equations, and how we think about these two solutions as being an example of using the matrix inverse, it's called. Okay, so a matrix and a vector is something that it could be a column like this, where it has entries like this. It could be a row like this. It could be a series of rows like this. It could be a series of columns, which is also the case in a series of rows. A matrix is just an array, but in this set of equations, we have arrays of a special size because of the size of the original equations. Here we have two inputs, two outputs, two variables, two unknowns. This is a 2 by 2 matrix equation, so it has a 2 by 2 matrix of coefficients, A, D, C, B. There are 4 elements here, 2 columns, 2 rows, 4 elements, and then there is a 1 by 2 and 1 by 2 for x and y respectively. So let's see what it looks like. I write y1 like this, y2 like this, and then here's my 2 by 2 matrix, which I'm going to fill in a second as I explain how multiplication works, x1 and x2. So notice that even though x1 and x2 are added together in this equation, I put them separately and like this, so that this and this have the same shape. I could have written it the other way, to have this be a row and this be a row. That would have also been fine, and I could have figured out where to put the matrix. But this is a simple way to do it that is the way we use most of the time. Okay, so now we need to understand this. Each of these coefficients, it looks almost like a dot product, if you're familiar with that, of a matrix AB dotted into x1, x2. And in fact, a single row or a single column matrix is a lot like a vector, and we're going to be able to jump back and forth between lists that are like vector lists and matrices that are either one row or one column, and relate those back and forth to vectors, because vectors and linear algebra are very closely related. So when we get to vectors and think about 3 dimensions or multiple dimensions, we will be able to relate those back to our linear algebra and take advantage of all the things we learned about solving equations with these kind of systems in that setting. Okay, cool. All right, so A times x1 and B times x2 are added together. So the first column here, first row here is going to represent the first equation, but it needs to draw on both the first row and the second row of this. So there's a particular symmetry in the way that you multiply, and this is a matrix multiplication between a 2 by 2 matrix and a 2 by 1 column matrix, like this. So this column is multiplied by the first row, so the first column multiplies the first row, and the sum of those, just like a dot product, the first row, first column, first row, first column, second row, first column, second column, first row, are added together to make a sum like this. So if I draw this in colors, the operation we're thinking of here is in this orientation like this. And then the second equation, which is going to be the second row of this, equal to the second row of this whole matrix, is like this times this. So Cx1, C times x1, D times x2, D times x2. So here the second row, first column, times the first row, first column, second row, second column, times the second row, first column, gives us this lower side of the equation. And just as things in this equation don't mess around with things in this equation, and things on this side of the equation don't mess around with things in this side of the equation as it's written here, each of the rows on the left side is equal to the row on the right side after we do that matrix multiplication, which is this and this. So, but each of the rows here inside the x1, x2 contributes, because of the matrix multiplication, to both the upper row of the whole equation and the lower row of the whole equation. Okay, so if we were going to write this in matrix form, we might write it as y equals mx. And sometimes we put little vector signs on top of things. Sometimes we would make these symbols bold. We're going to use bold, which is a little bit more like what's in the notes. And remember, the last time we wrote y equals mx, we said, oh, it's trivial to solve that. Let's just write m inverse times y equals x. This is for a one-dimensional equation with just one unknown x, one unknown y. So this is a 1 by 1 matrix. This is a 1 by 1 matrix. This is a 1 by 1 matrix. And then we can associate the inverse of this m with just 1 over m. Is the same true here? Well, no, we can't. Well, I guess so, in the sense that we could write this as m, the matrix, to the minus 1, its inverse, times y, the matrix, equals x, if only we could figure out what this m matrix was. Well, now look, this is very similar to this in that there's a matrix operating on y. Y is a 2 by 1 column. X is a 2 by 1 column. So this matrix here, just counting out how it worked, is also going to have to be a 2 by 2 matrix. But what matrix is it? Well, we actually already have the answer written down here in these two solutions where we solve these two equations to find x1 and x2. So let's see. So x1 goes here. So the x1, x2 become the rows of the right-hand side of the rows in this equation. And now y is actually unchanged from here to here. It's just the m that moved, not the y. So we can copy the y from there, y1, y2. It's just a column like that. And then there's a matrix here, which is the inverse of m. And what's the inverse of m? Well, we actually already found the inverse by solving these equations. So let's see what it has to be. What's the part that multiplies by y1? Well, actually this is going to be a little messy. Let's do ourselves a favor and write out the scalar out front that is 1 over the determinant, because that's in both parts of these. So when I write a scalar out front, I mean it's going to apply to every row in this equation. And now we just need to figure out the elements of this matrix. So y1 appears here in the numerator with a d out front. So d times y1 minus b times y2. That takes care, let me make that a little bit more clear that that's not next to each other. Those are two separate elements of this matrix. And then down here, minus c, a. Hey, look, this thing is the inverse of a matrix M, and M is A, B, C, D. M inverse is D minus B minus C, A. So we swap the order of the ones on the diagonal. We make the ones on the off diagonal, this direction, negative, and we divide by the determinant. And that gives us the matrix inverse for a 2 by 2 matrix. This always solves every set of 2 by 2 equations as long as the determinant is not equal to 0.